Okay, good morning, everyone. In the last class, we had discussed about ionic or electrovalent bond, right? Ionic or electrovalent bond, the limitations of octet rule. Do you remember what are the limitations of octet rule? Devika, can you tell me?
Ma'am, noble gases form compounds with oxygen and chlorine. Then this theory does not account for the shape of the molecule and does not explain the stability of the atom.
These are the drawbacks of octet theory, right? And there are certain limitations also. According to octet rule, we have learned that after the involvement of chemical bonding, each atom will obtain 8 electrons in their outermost shell. But we have learned certain exceptions, right? In the case of some compounds, the number of electrons surrounding the central atom is less than 8. In some cases, it will be more than 8. Then more than 8, it is known as expanded octet. When the total number of valence electron is odd, 8 valence electrons will not be there. Okay, so these are the limitations of octet rule. Then we have covered this drawbacks of octet theory. Then what about this ionic or electrovalent bond? What is that? Nimida?
When a bond is formed.
1 minute, children. Okay, tell me.
When a bond is formed by the transfer of electrons,
Yes.
8 electrons.
The bond formed between the due to the transfer of electrons. Either one atom will donate electron and other will accept electron, right? And a strong electrostatic force of attraction that will hold these two ions. That's it. Okay. Then now we are going to learn about bond parameters. Okay. There are certain parameters that helps to measure the bond. So first one, we will start with bond length. Okay. Bond length. So bond length, that is calculated as the equilibrium distance between the centers of the nuclei of the two bonded atoms. It is called bond length. Clear, children? The equilibrium distance between the centers of the nuclei of two bonded atoms is called its bond length. You know that there are two types of bonding, ionic bonding and covalent bonding. If two atoms, they are joined together or bonded together either by ionic bond or covalent bond, the equilibrium distance between the centers of these two bonded atoms, it is called its bond length. Clear? And related to this bond length, we will learn certain types of radius that we have already learned in the previous chapter, that is covalent radius, then van der Waals radius, metallic radius, etc. Okay. So this bond length, it is the equilibrium distance between the centers of the two nuclei of two bonded atoms. If two atoms, they are bonded together either by ionic bond or covalent bonding, the distance between the two centers, it is considered as the bond length. Clear, children? Yes. Okay. Jewel, can you please read?
Yes, ma'am.
Yes.
The equilibrium distance between the centers of the nuclei of two bonded atoms is called its bond length.
Okay. Centers of the two nuclei of the two bonded atoms is called its bond length. This bond length, it can be measured by certain spectroscopic methods, then X-ray diffraction methods, then electron diffraction methods, etc. Electron diffraction methods, etc. Okay, so this bond length, it can be measured using spectroscopic methods, X-ray diffraction methods, electron diffraction methods, etc. Clear, children? Okay, then related to this bond length, now we are going to learn about covalent radius, then electrovalent radius, etc. That is van der Waals radius, etc. Have we completed this one? So Malavika, which are the methods to find out the bond length?
Spectroscopic method, X-ray diffraction, and electron diffraction method.
Okay. So next one, covalent radius. Yeah. Yes,
Yeah,
yes.
okay.
Okay, okay.
Okay.
Okay. Then we are moving to covalent radius. This covalent radius is measured approximately as the radius of an atom's core, which is in contact, it's contact with the core of an adjacent atom in a bonded situation. During bonding, two atoms will be bonded together either by ionic bond or covalent bonding, right? There will be some force of attraction between these two atoms. So here this covalent radius, it is measured approximately as the radius of an atom's core. Atom's core means it's other than the outermost shell, that is considered as the core. Nucleus with the inner shell, that is core. Okay, so the covalent radius, it is measured approximately as the radius of an atom's core, which is in contact with the core of an adjacent atom in a bonded situation. Here in this bonding, already the outermost shell that take part in chemical reaction, right? That's why the core is considered. Clear, children? In the case of outermost shell, it will involved in chemical bonding, either by transfer of electrons or by sharing of electrons. So the core will remain there. Core contains nucleus and inner shells. So the covalent radius is measured approximately as the radius of an atom's core, which is in contact with the core of an adjacent atom in a bonded situation. Or otherwise, we can define this covalent radius. It is the half of the distance between the two similar atoms joined by a covalent bond in the same molecule. So we can also calculate it as half the distance between the two centers. Half the distance between the two centers. That is also calculated as covalent radius. So there are two methods for calculating this covalent radius. In the first one, we will measure the radius of one atom's core with another one. Or we can find out the half of the distance between the centers of two bonded atoms in a molecule. Half of this distance. Okay. That's about covalent radius. And this covalent radius, it's related to covalent bonding. Covalent bonding. Covalent bonding.
Ma'am,
Yeah.
will you repeat the first point again?
Sure. I told you there will be, we can consider this atom as two parts, right? An outside shell or the outermost shell and the inner core. Inner core means nucleus plus inner shells. Clear? And in the during the chemical bonding, this outer shell that is involved in bonding. So we will not consider this outer shell. Only the inner shells and nucleus will be there in bonding. Okay. Clear, children?
Yes, ma'am.
Okay. Have you completed this one?
No, ma'am.
Okay, then you can complete.
Yes, ma'am.
Yes, all of you. Okay, so when we are considering two atoms, wait. Okay, atom A and atom B. Atom A and atom B. This is considered as the radius RA, right? RA. and this will be considered as RB. Okay, this bond length is calculated as R, that is RA plus RB, that is bond length. Okay, and in this case, the covalent radius of A, that is equal to RA, then covalent radius of B, that is RB. RB. This is clear, children? Yes, okay. Then we are moving to the next one, that is, wait. That is van der Waals radius. Okay, next one is van der Waals radius. So the main difference between van der Waals radius and covalent radius, here we are also considering this valence shell in a non-bonded situation. Okay, in the previous case, we just considered only the core, that means nucleus and the inner shells, right? Here, in the case of van der Waals radius, it represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Okay, the van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. And this van der Waals radius is also half of the distance between two similar atoms in separate molecules in a solid. The van der Waals radius, it represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Even in non-bonded situation, we can calculate this van der Waals radius. The van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. Okay, that's about bond length. Okay. So that's the internuclear distance between two atoms in a molecule. We can measure it in the terms of covalent radius and van der Waals radius. Covalent radius, it is related to covalent bonding. That means the sharing of electrons. In the case of covalent radius, we will only consider the core of core. Okay, core includes the nucleus and inner shells, and we will avoid this outermost shell. Then van der Waals radius, it will represent the overall size of the atom, which includes its valence shell in a non-bonded situation. Here also it's the half the distance between two similar atoms in separate molecules in a solid. Children, all of you, please switch on your videos. Have you completed this one?
No.
Okay.
Yes, ma'am.
Yes. Then we are moving to the next bond parameter. That is, yeah, before that, factors affecting the bond length. Factors affecting bond length. First one about size of the atoms. Okay, size of the atoms. So the bond length increases with increase in the size of the atoms. In a group, when we are moving from top to bottom, their size increases. Due to additional shells will be added there, right? So here also the size of the atoms increases in a group. Along with that, bond length increases. Clear? The bond length increases with increase in the size of the atoms. When we are considering the group 17 halogens, it's from fluorine, chlorine, then bromine, iodine, etc. Here the order is that Hi, that is hydrogen iodide, it will be greater than HBr, then HCl, HF, etc. So when we are moving from top to bottom in a group, their size increases. Along with their size, this bond length also increases. So the first factor that affecting bond length, that is size of the atoms. Clear? Then the second one about multiplicity of bond. Okay, multiplicity of bond. The bond length decreases with the multiplicity of bond. If they are multiple bonds, the double bond, triple bond, etc., this bond length decreases. So this single bond, it has the maximum bond length. Okay, when it comes to double bond and triple bond, this bond length decreases. So the second factor that affecting bond length is multiplicity of bond. The bond length decreases with the multiplicity of the bond. This bond length of carbon-carbon bonds are in the order carbon-carbon triple bond, it is less than carbon-carbon double bond. It is less than carbon-carbon single bond. So bond length is more in single bonds. Okay. Yes. So first one is size of the atoms. Second one, multiplicity of bond. Navneet, can you please read the slide?
Yes, ma'am.
Yes.
Size of the atoms. The bond length increases with increase in size of the atom. For example, bond length of HX are in the order HI greater than
Yes.
greater than HBr greater than HCl greater than HF.
Okay.
Multiplicity of bond. The bond length increases with the multiplicity
Decreases. Bond length decreases.
with the multiplicity of bond. Thus, bond length of carbon-carbon bonds are in the order C triple bond, C less than C double bond, C less than C single bond.
Okay, okay. Have you completed, children?
Yes,
All of
ma'am.
you? Adulya?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, okay. Then we are moving to the second bond parameter, that's bond angle. Okay, bond angle. So here, the angle between the orbitals containing the bonding electron pairs around the central atom in a molecule or complex ion, it is called the bond angle. Okay, the angle between the orbitals containing the bonding electron pairs. So here you can see this oxygen is bonded with 2 hydrogen atoms, right? So the angle between the orbitals containing the bonding electron pairs. So here the bonding electron pairs exist between oxygen and hydrogen, isn't it? So the angle between the orbitals containing the bonding electron pairs around the central atom in a molecule or complex ion, it is called bond angle. So here the bond angle between hydrogen, oxygen, hydrogen, that is 104.45 degree. So this is the second bond parameter. First one is bond length, second one is bond angle. Okay, the angle between the orbitals containing the bonding electron pairs around the central atom in a molecule or complex ion. It is called the bond angle. We usually expressed it in degree. Okay, bond angle, it is expressed in degree. It can also be find out using certain spectroscopic methods. Spectroscopic methods. In the case of bond length also, we depend on spectroscopic methods, then electron diffraction, X-ray diffraction, etc. Right? Here we depend on spectroscopic methods to find out the bond angle of each molecule or ion. And this bond angle also helps us to determine its shape. Okay? When we know the, when we can able to identify the bond angle and bond length, we can estimate its shape of that molecule. So it also helps to find out the shape. Shape of a molecule. This is the bond angle of H2O molecule. H2O, 104.45 degree. 104.45 degree. Navrin, can you please read the slide about bond angle?
Yeah, ma'am. The angle between the orbitals containing the bonding electron pairs around the central atom in a molecule or complex ion is called the bond angle.
Okay.
And it helps to find the shape
Hmm.
and using
Represented in degree. Yes. Then find out using spectroscopic methods. Okay, have we completed this one? So this is the second bond parameter, bond angle. Have we completed, children?
Yes, ma'am.
Switch on your videos. Then third one, that is bond enthalpy. Bond enthalpy. Enthalpy means energy. Okay, energy. So here the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state is called bond dissociation enthalpy or simply bond enthalpy. So the amount of energy required to break the bond between two atoms in a gaseous state, it is called bond enthalpy or bond dissociation enthalpy. So in the case of this H2 hydrogen molecule, it will be dissociate into two hydrogen atoms, right? Two hydrogen atoms. So here the energy required to break the bond between two hydrogen atoms, that is 435.8 kilojoule per mole. So this much energy will be required for this hydrogen molecule to dissociate into two hydrogen atoms. Usually we are using this kilojoule per mole as its unit. Okay, kilojoule per mole. You can also write this unit of bond enthalpy is kilojoule per mole. Kilojoule per mole. The amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state is called bond dissociation enthalpy, or simply bond enthalpy. Here the molecules are in gaseous state. Okay, this converted to gaseous atoms. If the bond between two atoms will be very much stronger, high energy, that means high bond enthalpy should be needed to break that bond. Okay, the bond between two atoms will be very much stronger. High energy should be supplied for that molecule to dissociate into two atoms in gaseous state. Tushar, can you please read the slide?
Yes, ma'am. The amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state is called bond dissociation enthalpy, or simply bond enthalpy.
Okay. The unit of bond enthalpy, that is kilojoule per mole. Have you completed, children?
Yes, ma'am.
Yes. So here also there are certain factors that are affecting bond enthalpy. First one, the same size of the atoms. Okay, greater the size of the atoms, greater is the bond length, and less is the bond dissociation enthalpy. Here this bond enthalpy and bond length, they are inversely proportional. Okay, greater the size of the atom, greater will be the bond length, but less is the bond dissociation enthalpy. That is, less is the bond strength. The bond length is greater, that means they have lesser bond strength and only small amount of energy required to break that bond. You know that compared to single bonds, this multiple bonds are very much stronger, right? Their bond length is less, but they are very strong. So high energy should be supplied to break such bonds. Clear? So that's about the first point, size of the atoms. Greater the size of the atoms, greater is the bond length and less is the bond dissociation enthalpy. And less is the bond strength. And the second one is about multiplicity of bonds. For the bond between the same two atoms, greater is the multiplicity of bond, greater is the bond dissociation enthalpy. In terms of bond length, we have discussed that if multiplicity of bonds increases, bond length decreases. But here it is directly proportional. That means if multiplicity of bonds increases, the bond association enthalpy also increases. It will be very difficult to break the bonds between double bond and single bond compared to, double bond and triple bond compared to single bond. So for the bond between the same two atoms, greater is the multiplicity of the bond, greater is the bond dissociation enthalpy. For example, the bond dissociation enthalpies of H2, O2 and N2 are in the order. In the case of single bond between hydrogen, it will be less than double bond between oxygen and oxygen. It is less than triple bond between nitrogen and nitrogen. So more energy should be needed to break multiple bonds compared to single bond. Thomson, can you read the factors affecting the bond enthalpy?
Yes, ma'am. Size of the atoms. Greater the size of the atoms, greater is the bond length, and less is the bond dissociation enthalpy. That is less is the bond strength. Multiplicity of bonds. For the bond between the same two atoms, greater is the multiplicity of the bond. Greater is the bond dissociation enthalpy. For example, bond dissociation enthalpies of H2O2 and N2 are in the order H single bond, H less than, O double bond, O less than, N triple bond N.
Yes, okay. Completed, children?
Yes, ma'am.
All of you?
Yeah.
Yes, right? Okay,
Yeah.
then one more factor is there. That's about number of lone pairs of electrons present. Okay, number of lone pairs of electrons present. What is lone pair? Lone pair is the
Non-bonding.
non-bonding pair, right? Yes. Lone pair, that is the non-bonding pair of electrons. Electrons. So the number of lone pairs of electrons present. Greater the number of lone pairs of electrons present on the bonded atoms, greater is the repulsion between the atoms, and hence less is the bond association enthalpy. If there are more number of lone pairs present on an atom, greater is the repulsion between these electrons present in the atom. Okay, and hence less is the bond dissociation enthalpy. So only less amount of energy required to break that bond. Already repulsion exists between the atoms due to the presence of this lone pair. So very small amount of energy should be needed to break that bond. So that's the point. Greater the number of lone pairs of electrons present on the bonded atoms, greater is the repulsion between the atoms, and hence less is the bond dissociation enthalpy. So the three factors that affecting bond enthalpy: first one, size of the atom; second one, multiplicity of bond; third one, number of lone pairs of electrons present. Lakshmi, can you read the third point? Third factor that affecting the bond enthalpy.
Number of the lone pairs of the electrons present, greater the number of the lone pairs of electrons present on the bonded atoms, greater is the repulsion between the atoms, and hence less is the bond dissociation enthalpy.
Okay. Have we completed this point? Children?
Yes, ma'am.
All of you, right? Yes, okay. Then before moving to bond order, in the case of polyatomic ions or polyatomic molecules, okay, sometimes there will be no, one step is not sufficient for breaking the bonds between the atoms. sometimes 2 or 3 steps there. Okay. In the first step, some bond will be breaks, and in another step, another bond will be breaks. So it will follows different steps to break the bond between the atoms. In such cases, the energy required to break the bonds in each step will be different. Okay, not the same. In such cases, we will calculate the mean or average bond enthalpy as the total bond enthalpy. Clear, children? In the case of polyatomic ions or molecules, one step is not sufficient for breaking the bond between the atoms. So it will take place in different steps. And the energy required to break the bonds between the different atoms in different steps, that's not same. In such cases, we will take the average or mean bond enthalpy to break the energy required to break the bonds. Clear? This is clear, children? Yes. Then there is one more bond parameter, that is bond order. Bond order. Third one. Fourth one, right? Yes, fourth one. Bond length, bond angle, bond enthalpy, then bond order. In the Lewis representation of a molecule or ion, the number of bonds present between two atoms is called bond order. Clear, children? We are representing the electrons around the atom in Lewis structures, right? In this Lewis representation of a molecule or ion, the number of bonds present between two atoms, it is called bond order. For example, the bond orders of few molecules are given here. I told you each bond will share 2 pair of electrons, right? 2 pair of electrons. So the number of bond is calculated as the bond order. Clear? So here you can see between these two hydrogen atoms, there is one bond. So its bond order is 1. In the case of oxygen, double bond exists between the oxygen atoms. So its bond order is 2. Then in nitrogen atom, triple bond exists between these two nitrogen atoms. So its bond order is 3. Then in carbon monoxide also the same. Triple bond exists between carbon and oxygen. So it is 3. So the number of bonds present between two atoms, it is considered as the bond order of that molecule. The Lewis representation of a molecule or ion, the number of bonds present between two atoms is called bond order. For example, the bond orders of a few molecules are given below. Molecule H2, that is 1, then O2, it's 2, N2, that is 3, then CO, carbon monoxide, it's 3. Have you completed, children? Yes. Yes, then one more thing, that's about isoelectronic species. Okay, isoelectronic molecules or ions, they have same bond order. So you can note this point. Isoelectronic molecules and ions. Ions have same bond order. Okay. The previous example itself, you can see that in the case of N2 and CO. What will be the total number of electrons in N2 molecule? Isoelectronic species means the molecules or ions with same number of electrons, right? In the case of N2 molecule, what will be the total number of electrons? Yes. In each nitrogen atom, 7, right? So it will be 40. Here also in the case of carbon, it is 6. Then oxygen, 8. Here also, it's 40. The previous example itself, you can see that triple bond exists between N2 molecule. Carbon monoxide also, same. So here the bond order is 3, 4, both of this species. Okay. So for isoelectronic molecules and ions have same bond order. Clear, children? Yes. So these are the bond parameters. Which are they? Niranjan, can you tell me the bond parameters? Starting from bond length. Yes.
Bond length, bond angle, bond enthalpy, bond order.
Okay, bond order. So these are the different bond parameters. You have to learn its definition, method to find out this bond parameters, then factors affecting these bond parameters. Okay, then we can discuss the remaining things in the next class. So let me take your attendance. Just wait. Okay, then thank you all. See you in the next class. Bye.
Thank you, ma'am.
Thank you.
Thank you, ma'am.